Welcome to The Explainer. Today, we're going to peel back the layers on one of the most powerful ideas for making sense of our world, modeling. We're talking about everything from the behavior of a single cell all the way up to the future of our climate and how we can find the hidden logic in all that staggering complexity. So, let's start right here with this really fascinating image. What you're looking at are thousands of individual slime mold cells. Now, when there's plenty of food around, they just do their own thing, acting like single independent amoebae. But when the food starts to run out, something pretty wild happens. They start moving together, coordinating their actions. And here's the kicker. There's no leader, no central command. So how on earth does that happen, right? How does all this order just bubble up out of what looks like total chaos? Well, to understand this, we need a special kind of map of the world, a model. And it's the key to unlocking not just this mystery, but so many others. Now, here's something that's absolutely crucial to get. A model isn't the real thing. I mean, you'd never mistake a roadmap for the actual highway, right? A model is a simplification. It's a guide that intentionally leaves out all the unnecessary details so we can see the deep underlying structure and actually navigate the complexities of reality. To create one of these maps, modelers follow a process that might look familiar on the surface, but it has this really fascinating and deeply creative twist to it. Let's dig in. You know, we tend to think of science as this purely objective, just the facts kind of thing. But the very heart of building a model, well, it turns out it's a surprisingly personal and, frankly, artistic process. We all remember learning the scientific method in school, don't we? It's this beautiful, logical framework for discovery. You observe something, you come up with a hypothesis, you make a prediction, and then you test it. Seems pretty straightforward, but there's a catch. See, when you're trying to model a really complex system, one of these steps is, well, it's way more of an art than it is a science. Any idea which one it is? Yep, it's step 2, developing the hypothesis. This is where the artistry really comes into play. Figuring out the core rules of the model, like what factors do you even include? What do you ignore? That's not something you can just look up in a textbook. It literally springs from the modeler's own unique intellect, their personal experience, and their entire way of seeing the world. And that's really the key, right? The goal isn't to create a perfect one-to-one replica of reality. That would be impossible. The real goal is to create a model that's simple enough for us to actually understand, that's valid, meaning it matches what we observe in the real world, and that's robust, so it doesn't just fall apart if you tweak a few of the assumptions. It's a search for elegance and power. Of course, not all maps are built the same way. A subway map is totally different from a topographical map of a mountain range, and they serve completely different purposes. Well, the same thing is true for models. So let's take a quick peek at a few tools in the modeler's kit. So you have some models like game theory, which famously got its start during the Cold War. It's all about understanding strategic decision-making. And it's used absolutely everywhere, from economics trying to analyze markets to evolutionary biology trying to figure out animal behavior. Then you've got these other models that kind of flip the script and work from the bottom up. They're called agent-based models. This is where you program individual agents, just like our slime mold cells, with a few simple rules. And then you just sit back and watch what complex collective behavior pops out when they all interact with each other. And some models do something really cool. They strip away almost everything except for the connections. These network models reveal the hidden structures that link everything together, from your friends on social media to the proteins inside a cell. They show us that sometimes the most important thing isn't the individual parts, but the relationships between them. Okay, now we get to what I think is the most mind-bending part of all this. Sometimes the absolute simplest maps can lead us into the most surprising, unpredictable, and beautiful territories imaginable. Believe it or not, it can all start with a mathematical rule that looks this simple. Just this one clean, elegant curve. This is the famous logistic map, a classic example in chaos theory. The process itself is almost laughably simple. You take a number, you apply this rule to get a new number, and then you just feed that new number right back into the rule, again and again and again. You'd think that would give you a nice, predictable pattern, wouldn't you? Well, when you do that simple process over and over, you don't get a simple result at all. You get this, an infinitely complex, intricate, and fundamentally unpredictable pattern. This is a perfect example of what's called emergence, where this incredibly complex, system-wide behavior arises from individual little components just following a few very simple rules. It's where complexity is born from pure simplicity. And this right here is a brilliant illustration of the heart of chaos theory, which is often described as a process of stretching and folding. So imagine a tiny, almost immeasurable difference in your starting number. That's the microscopic information. Chaos takes that tiny difference and stretches it out until it becomes enormous, completely changing the long-term result. And the folding part, that just means the system stays within certain boundaries, endlessly mixing and remixing all the possibilities, but never ever repeating itself exactly. So, what's the point of all this? Why should we care about the art of modeling and the nature of chaos? What does this mean for us, really? It matters because these ideas connect that microscopic world of slime molds to the absolute biggest challenges we face, like our planet's climate. And this is where modeling becomes an indispensable tool. You see, chaos theory tells us we probably can't predict the exact weather on, say, June 5th, 100 years from now. That's the unpredictable part. But, and this is so important, chaos should not be an excuse to just throw our hands up and avoid making predictions. We can model and predict the long-term trends, the statistical properties of the system, like the change in average global temperature. And that, for me, is the most powerful idea of all. Models are so much more than just crystal balls for predicting the future. They're a new kind of lens. They give us a new language to find the hidden patterns in what just looks like random noise. They help us see the simple rules that might be driving the incredibly complex systems that are all around us every single day. And ultimately, learning to see the world like a modeler lets you ask one of the most profound questions there is. I mean, think about it. Think about traffic jams or stock market swings or even the way ideas spread online. What complex patterns in your world, when you really look at them, might just be the result of a few surprisingly simple rules playing out over and over and over again?